Welcome back, everybody, to Rikers Island ICND2 training course. We're going to be focusing on, in this video, is going to be port channels. So, what is a port channel? Well, a port channel, in a nutshell, is an aggregation of layer 2 and or layer 3 links. So basically, the idea here is in spanning tree protocol, we saw that ports were getting blocked based off of the root port election, the designated port election, things like that. Well, that can be detrimental to a network, especially if you've got, 10 gig or 40 gig links in the network. Nobody wants to have a really high speed port in a blocking mode because spanning tree wants to block a layer 2 connection or wants to block traffic from going out that interface because of the nature of the type of connection that it is. Well, port channels were created, or an ether channel, depending on how you want to look at it. They mean the same thing. Lags, link aggregation groups, MLAGs, multi-chassis link aggregation, things like that. They all mean the same thing at the end of the day. They all mean that you are taking links and you're in software, you're making them appear as a single connection. Even though you might have 4 or 8 or 16 of these links together, they all mean the same thing. So what it's doing is it's basically effectively lying to spanning tree protocol. You are configuring the lag to simply go in and say, you know what, the ports that I have identified to be in a port channel are now appearing to spanning tree as a single link. Now, that doesn't eliminate the blocking of ports, especially if you've got a loop still in the network. But if you have a situation where you have a switch that has a port channel up to a port channel up to one switch and a port channel up to another switch, but there's no layer 2 connectivity in between those two switches, then you can forward active because you have the connectivity in play to where it doesn't affect the there's no loop possible. And we'll talk about how that will come into play. I've actually got a demonstration for you that I'm going to walk you guys through to show you what that looks like. We're going to start off with a basic overview of what a port channel is in this video, and then we'll take a look at configuring layer 2 and then layer 3 port channels in separate videos. So the idea here with the port channel is being able to bundle the interfaces into groups so they appear as a single link. So the port channel itself becomes the interface that which spanning tree bases its path calculation off of. So whatever the total amount of links are in the port channel, that is going to be what spanning tree uses to define the cost. So if you've got 4 100 megabit interfaces bundled together, that's going to be a 400 megabit ether channel. So spanning tree will figure out, okay, what is the cost value for a 400 megabit port channel, and then make its that is going to be how it determines its cost based off of that. Now, one of the common misconceptions about port channels is that when you bundle the links together, that you now have 400 megabits of data to forward with. And that is simply not the case. What you're doing effectively with a port channel is you are providing redundancy between the links. So no recalculation has to occur. You're not actually leveraging the full bandwidth of all those links. You're not forwarding data over all 4 of them at the same time. You're only forwarding data off of one of those ports in that particular port channel. So it may appear as 400 megabits per second. It may appear as 4 gigabits per second. It may appear as 40 gigabits per second if you're bundling, 100 meg, gig, or 10 gig links together. But you're actually not getting 40 gigabits of throughput. It's a redundancy type thing. So if a link goes down, no path calculation has to be reran. Whether it's OSPF, whether it's BGP, whether it's spanning tree protocol, nothing has to change because a link failure isn't detected. The port channel is still up. So as long as at least one member out of however many members were in that port channel are still up, then the port channel itself is operational. So if you are I've walked into environments before where people are going, I should have 800 gigabits of throughput, or I'm sorry, 800 megabits of throughput. And I look at it and they got four 8 100 links running from a switch down to a server. And I'm like, nope, it's only 100 meg. And um, they're like, well, how do we get 800 megabits? Well, you're not going to get 800 megabits. There are some cheeky load balancing techniques you can use on the back end. So you can do ether channel load balancing and mess around with different capabilities. But at the end of the day, you still only have one link, and whatever the link speed is, that's how much data you're able to forward. So in this particular case, if you've got a 100 megabit connection, you might have 8 of them bundled together, but you're only able to forward over one of them. Now you could start playing around with some load balancing hashes and say, do some sort of mechanism in the back to where you don't always use the same link all the time. You can kind of load balance them across them and stuff like that. We're not going to get into that here in CCNA. We will take a look at that in CCNP because it's a little bit more advanced. But there are some load sharing options that are available to you. Now, one of the things that's also really important to understand is the port channel is it focuses on the links itself. What they're connected to is pretty much arbitrary. It doesn't really care. And the reason I say that is because I can have, let's say for instance, I have a 2-switch stack. Let's say I'm here in my office, I'm looking at two 3750s. I'm looking at a 3750 24 port and 48 port. When we get into chassis aggregation, I'm actually going to show you how that looks. I'll spin the switches up and I'll show you what they look like with a stack cable between them and how that comes into play. The idea here is if I have, let's say I have a downstream switch, or if I have a downstream server, is more applicable. What'll end up happening is if I team or bundle the interface, the NICs on that server together to appear as one connection, but I have two uplinks. Maybe I have one to the switch 1 and I have one to switch 2, and switch 1 and 2 are in a stack. If that's the case, then what will end up happening is if they're both layer 2 connections, I'll actually get what they call a MAC flap between the ports. I'll be learning the same MAC address on the two different links. And the reason why that's happening is from a spanning tree perspective, I will be seeing both ports as up because of the fact of they're connected down to a single device. Now, that's a bad thing because I don't want a MAC flap because then the ports are always going up and down, and then the MAC addresses are being learned. The switch is learning the same MAC address from two different ports. So the bad thing behind this is I don't know, or the switch doesn't know, okay, well, which port do I forward the traffic out towards? The switch is going to look at you, scratch its head, and say, I don't know. So what ends up happening is from the switch side, I can say, oh, you know what? Whatever ports that server connects to, let's say it's port 1/0/1 and 2/0/1 on the switch. They're attached to the same switch, but from a logical perspective, two different ports on the switch. But I'm learning the MAC address in on both. So now what I got to do is I have to, on the switch side, I have to basically say, you know what? I don't know which one's which, so I have to basically fool the switch into thinking it's coming from the same. So the idea here is actually really, really simple. We go ahead and bust out my pen pad real quick. And we can go ahead and grab the pen. The idea is something like this. Normally a port channel is going to operate something like this. I have a switch and I have a switch. And then I have a link between the two. And anytime you see this circle going around them, that indicates that that is a that's a port channel because you've got two acting as one. So think of it like this, where I can't change my color at the moment, but if I had this link here and this link here, 1 and 2 are going to be the members of that port channel, but we have port channel 1 has both ports 1 and 2 inside of it. So that's how you would view it from this perspective, from a logical perspective. This is the logical interface. 1 and 2 are the physical interfaces, but they're bounded together with the port channel. Now, let's say, going back to our server example, let's say I've got this server here, or this switch here, and then I have a server sitting down here. This guy connects to, let's say, switch 1 and switch 2. We got 2, we've got 1, we have 2. Let's say this is port 10 here, this is port 10 here. If on the back side we have a stacking cable, okay, so these look like one logical switch from a SSH or SNMP perspective. So you log in, you see the 1/0/10, and you see 2/0/10 would be the port numberings. Well, if this is MAC address A, I'm learning MAC address A on both ports. Well, which one do I forward the data out of? Well, unfortunately, with MAC addresses, you have to have a specific port because this right here and this right here would both be forwarding. So I need to figure out what it is that I need to forward the data out of. So what you do is you actually come in here and you would say, I'm going to create a port channel, or that's EL, port channel, and then I'll say port channel 1. And then what I do at the interface level, I type in int range 1/0/10 and 2/0/10, and I say channel group 1 mode is on, because I don't want to do any type of negotiation. We'll talk about negotiation here in a minute. I want to just bundle these two into channel group 1, and then port channel 1, I have my config. I don't have to do anything to it. It's just a logical interface. So channel group 1 maps to port channel 1. If you did not already have the port channel created, the channel group 1 would automatically create the port channel for you. So you have that. So now what will end up happening is this right here, this configuration here looks like this to the switch or to the server. There's two links coming up, but you have switch 1 here, and then you have server 1 here. It appears as one upstream switch from the server, and that's what they consider to be multi-chassis link aggregation, because you've got multiple chassis. The same thing happens with if you have a 6500 pair or a 48500 pair. Let's say these are 6500s. The same thing would happen with, and I don't want to get into chassis aggregation too deep, but I wanted to explain from a port channel perspective where this would come into play. If these guys have a VSL between them, which is a virtual switch link, you could run VSS, the virtual switching system. So this right here, you have 65091 and 65092, you have server 1. Well, when you VSS them together and they're port channeled from the switch side of the house, they also appear to look like switch 1 from this perspective. It appears as one big switch upstream with lots and lots of ports. And then the control plane mechanisms are synced and stuff like that. That is a general idea of how this stuff comes into play. So as long as you understand that portion of it, you're in really good shape. So what we want to focus on now is the back end stuff. So next step, the modes. You have 3 different modes. You have mode on, which is basically just saying on, no negotiation. You just want to turn it on. All the examples I just gave where we have a, whether it's one switch with 2 links to another switch, whether it's 2 switches that are multi-chassis ether channel, or you have like a 3750 stack, or you have a 6509 VSS, any of those scenarios, I would, if the remote end does not run LACP or what have you, I simply use mode on. If I need to make the from a switching perspective, I just need to make that a layer 2 link, I use mode on. It's the simplest configuration option of all. Then you have LACP, which is the Link Aggregation Control Protocol. This is the open standard 802.3 AD, and what it does is it works off of active passive. And what it basically is doing with active passive is active is saying, you know what, this is what I want to do. I want to negotiate a layer 2, or I want to negotiate a port channel with you using the Link Aggregation Control Protocol, or LACP. Some people call it Lacp. I don't really care what you coin the term or what term you use to identify it by, as long as you understand the concept of LACP is going to be your open standard. So if I have a Cisco switch and I have a VMware ESXi host, and I have a couple of links coming down that ESXi host, and I'm running those links that I connect to are attached to a distributed vSwitch port group, then I can bundle them together and have a bundle going up that's LACP negotiated. If I am running, for instance, if I'm running Nexus 7000 or Nexus 5K and I'm running down towards a server and I want to run maybe over a FEX pair and I want to run LACP to negotiate over the FEX connections, I can do that as well. LACP gives you a lot of flexibility because a lot of other platforms support it. PAGP, or the Port Aggregation Protocol, is Cisco's proprietary implementation. This came out before LACP did, and I always list the open standard version first, simply for the fact of it makes more sense to me. This one works off of the same way the DTP does, or Dynamic Trunking Protocol. It uses desirable and auto. Desirable says I want to negotiate I'm going to negotiate PAGP with you. Auto says I'm going to do whatever you say. Same thing with passive. Passive says, you know what, I'm going to do whatever you say. There's a couple of correlations here we have to make real quick before we get into any of the other content. Active, active, active on are supported. Active, active, active passive, and active on are all supported configurations. Passive passive will not work because you're both waiting for somebody to tell you what to do. Same thing with PAGP. Desirable and desirable, desirable auto, desirable on are all supported configurations. This auto is you're waiting for somebody to tell you what to do, so the port will never come up. My preferred method of doing things, especially if you're doing Cisco to Cisco, I always choose on. I don't want to negotiate. I want you just to turn it on. I remove the negotiation aspect of things completely from the equation. I've worked with all three of them. I prefer on if I'm going to be, and that's just my preference, especially in a situation where I don't want to be port channeling down to the server. Maybe I don't want a port channel to the server. I just want a layer 2 link down to a layer 2 port on the server. That's going to act as an access port and not going to be trunking anything. Typically, the only time, and it really doesn't make much of a difference because port channels don't care if it is a trunk or a VLAN. It doesn't care. All it cares about is how am I connecting to you. So a port channel can be either a trunk link, so it can handle more than one VLAN tag at a time, or it can be VLAN based access, which is the example I'm working with, where if I only have one VLAN traversing that trunk link or that port channel at a time, and it connects down to a server, I don't need to give it a trunk access. So therefore, I don't need to me, just my opinion, why would I need to negotiate use a negotiation protocol to form a port channel? Let me just turn it on the switch side to make it look like one port channel, and then that goes down to the server. The server is none the wiser. Or you can make it layer 3. It can be routed. It really depends on your preference, where the connections between the switches are the switch ports are issued the no switch port command, which means it turns into a layer 3 port. Those links are then bundled into a channel group, and then the port channel receives an IP address. So what's kind of cool here is when you're setting this up, whether it's layer 2 or layer 3, there's a few things that have to match. The first thing that has to match is the speed and duplex have to be equal. You can't have a 100 meg on one side and a gigabit on the other. And you can't have a 100 meg link and a gigabit link in the same port channel. They are not compatible. They have to be the same speed, the same duplex. The other thing that has to match is you can't mix and match VLAN and trunk. It's one or the other. It's either VLAN access for a single VLAN, or it's trunk access for multiple VLANs. Now, you may only have one VLAN crossing that trunk, and with the intention of adding more VLANs later, but it has to be configured as such. So it's one or the other, not both. Same thing with routed. Routed, it's going to be once you type in no switch port at the link level, it's going to go ahead and turn that to a layer 3 port channel, and then you can apply an IP address to it. So a lot of capabilities that are out there for us to get stuff operational. So that is basically what I wanted to cover in this video, is just go over the high level stuff so that everybody's on the same page. This stuff is, port channels are very popular, especially in modern networks today where you need redundancy. So what's actually even cooler, in my opinion, is a lot of places are, especially if you get dual fiber links down to your switches, port channels are everywhere. I mean, I don't walk into an environment with dual 10 gig links or dual gigabit links that are uplinks without having a port channel. I port channel everything. And the reason for that is it gives you redundancy. Because and if you don't do this, we'll say you've got if you've got two layer 3 port channel or two layer 3 connections down to a switch. We'll say you're routing everywhere in your environment. Well, what's going to end up happening is if I have two layer 3 routed links from an access layer switch to a distribution layer switch, great. But if one of those links goes down, I have an IGP recalculation that's got to happen. That link failure has got to get detected, and then that information's got to get locally calculated by that device, and then it's got to get propagated throughout the rest of the network. So it's actually a rather involved 4-step process in order for that to happen. From a optimization perspective, if I would have just bundled those two links in the same port channel, whether they're layer 3 or layer 2 is irrelevant, I wouldn't have had to worry about that. Because if one of the two links goes down, it's still up. As long as at least one link in your port channel is operational, you're in good shape. Now, one of the cool things about port channels too is, well, actually, this is one of the cons or the negatives. When you're dealing with port channels, Cisco recommends you do port channels, or you configure them in bundles of 2, which means you have 2 links, 4 links, 8 links, etc. Don't do them in groups of 3. It tends to be the negotiation is goofy. There's some weird hashing issues that you run into. This is my experience as well. So whenever I'm bundling things, I do it in groups of 2. So and it doesn't matter where exactly the ports are. They don't have to be sitting right next to each other. You don't have to do ports 2 and 4 or 1 and 2 or 5 and 6. It could be port 1 and port 48. It does not matter. Unless the ports have some sort of mismatch between them. And if that's the case, the ports that can be port channeled will be, and they'll have a P, which means they're port channeled. Or you'll see a suspended, and suspended means that port's got some sort of issue attached to it, which could be a lot of different things. It could be a VLAN ID mismatch. It could be a speed issue, a duplex issue. It could be one of many things. But these are things to take a look at and understand as you're going forward. So that's pretty much the high level stuff. We'll start taking a look at getting our layer 2 port channels in place and operational in the next video, and walk you through the actual configuration and go from there. I hope this was informative for you guys. Thanks so much for your time and your patience. Until next time, guys, take it easy.